In this talk, I will talk about our paper Playing Unique Games on Certifiable Small Set Expanders. This is joint work with Boaz Barak, Pravesh Kothari, Sleel Shram, and David Stoiler. So, what is the unique games problem? An instance of the affine unique games problem on alphabet size k is a two-variate constraint satisfaction problem on n variables and m equations, which are all modulo k and which look like this. Each equation is of the form xi minus xj equal to sij, and it has to be satisfied modulo k. This particular form of some variable minus another variable is important. The affine unique games instance can also be viewed as a label graph instance where variables get mapped to vertices, the constraints get mapped to the edges, the shifts or the RHS of the constraints get mapped to labels on the edges, and any assignment to the equation view of the instance corresponds to a labeling of the vertices in k to the n. Without loss of generality, we think of every constraint as xi minus xj equal to s with I less than equal to j, so that we have a direct correspondence between the equation view and the graph view. And in this talk, we will only think about the graph view. The C, S affine UG instance, UG problem is the following. Given an instance of the unique games problem on alphabet k on n variables, such that with the promise that there exists an assignment that satisfies a C fraction of the equations, we are asked to find an assignment that satisfies at least an S fraction of the equations. The important thing here is that k is thought of as a constant, n grows asymptotically, and c and s are both constants smaller than 1, with c bigger than s. The unique games conjecture proposed by Coate in 2002 says the following. For all constants epsilon, there exists a large enough constant k such that the affine unique games problem with parameters 1 minus epsilon comma epsilon on alphabet size k is NP hard. So in words, this means that for epsilon, however tiny we choose, for example, 0.01, given a 0.99 satisfying assignment of UG, one cannot always find even a 0.01 satisfying solution to the instance efficiently. It turns out that the unique games conjecture has some very striking consequences. It implies optimal hardness of approximation results for combinatorial optimization problems, such as vertex cover, max cut, and all CSPs. So what do we know about the UGC itself? On the hardness side, a series of recent works by Dinur, Coate, Kindler, Minzer, and Safra showed that the unique games problem with parameters half and epsilon is NP hard. This is also known in the literature as 1 minus epsilon comma epsilon 2 to 2 games problem. Although this implies some hardness of approximation results, it is not sufficient to yield all the consequences of the UGC, and it turns out to be significantly weaker than the UGC. So now let's see what's known on the algorithm side. It is known that all unique games instances have sub-exponential time algorithms. That is, the unique games problem with parameters 1 minus epsilon and epsilon can be solved in time 2 to the n to the poly and epsilon. Furthermore, better results are known for restricted families of instances of unique games. These include expander graphs, perturbed random graphs, and graphs with small threshold rank, and any UG instance on such graphs. These algorithms emphasize the difference between hard CSPs such as 3-SAT, for which we do not know any polytime algorithms on restricted families. These results constitute the best known evidence against the truth of the UGC. Today, we will discuss algorithms for UG and, moreover, a specific class of algorithms known as the sum of squares algorithms. The sum of squares hierarchy, or the Lasserre-Parello hierarchy, is a hierarchy of increasingly powerful semi-definite programming relaxations for polynomial optimization. Notice that one can write the objective function for any CSP, such as maximizing the number of satisfied clauses in a 3-SAT formula, or maximizing the number of equations satisfied in a UG instance, as optimizing some polynomial over the Boolean hypercube. The SOS hierarchy is a convex relaxation of increasing complexity, denoted by its degree. Roughly, the degree of an SOS relaxation is the maximum degree of the polynomials involved in the relaxation. The degree can range from degree 2 to degree n, where n is the number of variables in the CSP. Solving the degree D SOS program for an optimization problem gives us an object called the degree D pseudo distribution, using which we need to produce a true solution to the problem. The procedure of going from a pseudo distribution to a solution to the optimization problem is known as rounding the pseudo distribution. Roughly, we can think of this as solving the SOS program yields a distribution over solutions to the optimization problem, but we are not allowed to sample from this distribution. Instead, we need to produce a solution using only the low degree D moments of the distribution. A related concept is that of sum of squares proofs. The low degree sum of squares proof system is a restricted proof system for proving polynomial inequalities. For example, think of the polynomial inequality x squared plus y squared greater equal 0 for x, y taking values in the reals. This is of course true and always satisfied. And indeed, this has an SOS proof because it is the sum of squares of two polynomials. Again, here we have the concept of a degree of the proof, which measures the complexity of the proof and can range from degree 2 to degree n. The degree of the proof we discussed for x squared plus y squared greater equal 0 is 2, because the degree of the polynomials involved in the proof is 2. SOS proofs and SOS algorithms are intimately connected, and this connection has been exploited to obtain efficient algorithms for a variety of problems, which we will see later. If you did not follow this part, feel free to ignore it and think of an SOS algorithm as a black box that spits out the low degree moments of a distribution over solutions to some problem. And what we need to do is take this distribution and round it to a solution to the problem, but only using the low degree moments. Now let us look at another concept which will be very important in studying unique games. As we saw earlier, unique games is known to be easy on expander graphs, but in fact, on a larger class of graphs known as small set expanders, it is conjectured to be hard. This is known to be equivalent to an important complexity theory conjecture known as the small set expansion hypothesis. And the UGC and the SSEH, small set expansion hypothesis, are very closely related. Therefore, it turns out to be very important to study graph expansion in the context of UG. Let us now recall the definitions for expansion in graphs. Given a D-regular graph, the expansion of a set in the graph is defined as the fraction of edges crossing the set, that is leaving the set, counted in the total number of edges incident on the set. So that is edges between S and the complement of S divided by D times the size of S. This notion leads to an important class of graphs known as expander graphs. G is said to be an epsilon expander graph if all sets S of size at most n by 2 have expansion at least epsilon. A larger class of graphs known as small set expanders is the following. G is said to be an epsilon delta small set expander if all sets of size at most delta n have expansion at least epsilon. The only difference between these two definitions is the set size requirement. In the latter definition, we have a really relaxed requirement because we only want small sets to expand and we do not care whether large sets expand or not. And hence, this turns out to be a larger class of graphs than expander graphs. The notion we consider in our paper is that of certifiable small set expanders. G is said to be an epsilon delta D certifiable small set expander if G is an epsilon delta small set expander, and furthermore, there is a sum of squares proof of degree at most D of this fact. To elaborate more, note that the property that G is a small set expander can be written as a polynomial inequality in some variables that take Boolean values. What we want here is that this polynomial inequality has a low degree sum of squares proof. Now I will elaborate on our main results. Firstly, we give polynomial time SOS algorithms for approximating unique games instances over certifiable small set expanders. Note here that this is not for all small set expanders, which would refute the SSEH, but only for certifiable small set expanders. We also give polynomial time SOS algorithms for approximating UG instances over Johnson graphs. Johnson graphs are not small set expanders, but they have a nice characterization of all the non-expanding sets. And we are somehow able to use this characterization, and I will elaborate on this more later. So why at all study these restricted instances? As is the case with 3SAT, contrary to it, no hard instances of unique games are known. UG is known to be easy on random graphs and on random instances, which correspond to expander graphs, and on perturbed random instances. Contrast this with 3SAT, for which random instances are conjectured to be hard at the satisfiability threshold. The algorithms for unique games on certifiable SSE graphs that we give imply a new connection between graph expansion and unique games, thus relating and deepening the connection between the UGC and the SSEH. Furthermore, the Johnson and Grassmann graphs were used in the construction of NP-hard instances for 2-to-2 games. The characterization of non-expanding sets that they proved is used by us to give algorithms for UG, highlighting a fascinating interplay between the use of instance structure in algorithms and hardness. So what is the relation between SOS algorithms and the unique games problem? Raghavendra showed that the UGC implies that the basic SDP, or the lowest level degree 2 sum of squares algorithm, is the optimal polytime algorithm for all CSPs. This led to efforts to refute the UGC using higher degree sum of squares algorithms. for unique games. The algorithms developed for UG led to a lot of techniques such as the global correlation rounding of BRS and the proof of two algorithm perspective of BBHKHC. These techniques have not only provided deep insights into the unique games problem, but also led to numerous algorithmic breakthroughs in high dimensional statistics, tensor decomposition, quantum computation, statistical physics, and more. In the light of all this, we give a new technique for rounding higher degree sum of squares relaxation for unique games. Not many techniques are known for rounding higher degree SOS relaxations. We show that polynomial sized SOS relaxations solve UG on graphs out of reach of previous techniques, such as the short code graphs, the noisy hypercube, and the Johnson graphs. Previous algorithms of BRS and ABS required quasi-polynomial time for the noisy hypercube and sub-exponential time for the short code and the Johnson graphs. We note that the noisy hypercube and the short code graphs are in fact small set expanders, and we crucially use this fact and the fact that they have a degree 4 sum of squares proof of small set expansion to give an algorithm for unique games on these graphs. So let's go into our main result in more detail. What we prove for certifiable SSE graphs is this. For all constants epsilon delta, degree D, alphabet size K, and every graph G, that is a certifiable SSE graph with these parameters, take any instance of affine unique games on G, that is 1 minus epsilon satisfiable. Then there is a polytime algorithm that finds a good satisfying assignment in time polynomial in the size of the graph. The exponent of this polynomial only depends on epsilon, delta, and D. Moreover, I would like to highlight here that the approximation ratio is independent of the alphabet size, which is a requirement for any non-trivial UG algorithm. And the completeness parameter epsilon is independent of the parameter delta. So our result works for all epsilon and delta, which means that it works for graphs that may not be expanders, but are small set expanders. Now I will highlight some main ideas that went into the proof of this theorem. Firstly, let's see what the algorithm looks like. Recall that we are given an instance of the affine unique games problem, which is 1 minus epsilon satisfiable, and G is an epsilon delta D certifiable small set expander. We need to return an assignment Y that satisfies a constant fraction of the constraints in expectation over the randomization that the algorithm might use. So our first step is to solve the degree D sum of squares program for instance I to obtain a 1 minus epsilon value degree D pseudo distribution mu for the instance I. Recall that what we can, even if you don't know about pseudo distributions, what this means is that roughly we are getting some distribution over satisfying assignments of the instance, but only access to the low degree moments of this distribution, and so no sampling access to mu. Now we will show how one can produce a good solution using only the low degree moments of this distribution. We will perform a very simple rounding procedure, which in fact uses only the first 2 moments of mu. Firstly, sample a random vertex from the graph and a random label in 0 to k minus 1, and condition the distribution on the event that the vertex U takes the label L. to obtain the new condition pseudo-distribution mu subscript u. Here the notation x subscript u equal to L just means that the value assigned to the vertex u is equal to L. Next, sample a solution X. Sample a solution to every other vertex V not equal to U by choosing its labels independently according to its marginals. So go over all the vertices and independently just sample from this conditioned distribution. So now let's see how we can use the expansion of G to our benefit. First, just as a thought experiment, consider two assignments X and X prime, and consider the following partition of the vertices of the graph. The component C0, defined using X and X prime, contains all the vertices U for which the label assigned to U by X, by the assignment X, minus the label assigned to U by the assignment X prime is 0 mod K. Similarly for C1, we want this difference to be 1 mod K, and so on. One can easily see that each vertex is assigned to one and only one of the components, and hence this is a valid partition of the vertices. Our main observation is that any edge between the component Ci and Cj for I not equal to j is violated by at least one of the assignments X or X prime. So to see this, first notice that if U belong to component Ci, we have that xu minus xu prime is I. And if V belongs to J, so xv minus xv prime is J. Now subtracting these two equations, we get that xu minus xv minus xu prime minus xv prime. So this quantity can be reinterpreted as the edge, the value on of the edge uv in component assignment X minus the label assigned to the edge uv in assignment X prime is equal to I minus j, and it's not equal to 0. Now suppose that this edge was satisfied by both the assignments. This edge would be equal to, this edge would be assigned the label prescribed by the label on the instance, and it would be same for both the assignments. And hence the subtraction of these quantities would give 0. So we know that this edge is violated in at least one of the assignments. Now, by the property that the assignments are 1 minus epsilon satisfying, there can be at most 2 epsilon fraction of edges that go between the shift parts, the parts in the shift partition. This is just by a simple union bound. Now, here we crucially use the expansion properties of G to show that at least one of the components in the shift partition must be at least delta in fractional size. And to see this, note that because of the small set expansion property of G, every small set of fractional size less than or equal to delta has expansion at least epsilon, and this holds for partitions too. A partition that has all sets of fractional size less than or equal to delta will have an epsilon fraction of edges crossing between the parts. This is a simple averaging argument. So by the contrapositive, we can conclude that there must be a large part of size at least delta if there are very few crossing edges. So far, this was a great thought experiment. We all, but we can make this formal in the following way. We define the following potential function. Take two assignments x and x prime uniformly from and independently from the distribution mu, and consider their shift partition, and consider the quantity which is sum of squares of the fractional sizes of the parts in the partition. So note that if there was one big part and nothing else, this quantity would be something like 1 for x and x prime. Whereas if there were really small small parts of all equal size, this quantity would be something like 1 over k. So this measures somewhat the average correlation between x and x prime, and some what we call the shift correlation. And in fact, using a similar proof to what we just did, we can show that this shift potential is large when we are on a certifiable small set expander, and mu is a degree D pseudo distribution. So we have that this potential of G on mu is at least delta. Now, the most interesting part is that we can use the fact that this potential is large and show that whenever this potential is large, the condition and round subroutine of algorithm 1 applied on this distribution outputs an assignment of value delta minus epsilon. So is this good enough for us? Unfortunately, no, because delta might be really smaller than epsilon. But this is handled by us using a more complicated shift partition potential function. There are a lot of technicalities that go into analyzing this, but thankfully this works out. I will just mention the main ideas in the Johnson graphs algorithms. The issue that we have to face is that Johnson graphs are not small set expanders. The nice thing though is that the structure of the non-expanding sets has a nice characterization. There exists a polynomial sized family F of induced subgraphs of Johnson graph such that every small set that is non-expanding is correlated with some non-expanding subgraph in this family F. Thanks for listening and hope you check out our paper for more details.